All right, so now we're going to review alkane reactions. So the good news is there's really only two of these, and it's the same reaction. So alkanes are pretty stable, and they're relatively boring in this class. Like, they don't have anything, no double bonds, no oxygens, no nitrogens, nothing interesting to make it super reactive. So there's really two reactions that we can do, chlorination and bromination, and they're really the same mechanism here. Okay, so Cl2 and light, or Br2 and light, let's start with Cl2 and light. So the fact that we have light and we have the halogen tells us that we're going to have some radical intermediate. So I'm going to go through how to predict the product here. I'm not going through the entire mechanisms of these because we've done those before. So you can go back and look at those things, but this is how to review these in terms of predicting the product. That's a nice summary of all of these. Okay, with Cl2 and light, chlorine is not nearly as picky as bromine, remember? So anywhere that there are hydrogens, so here, literally every carbon, as long as there is at least one hydrogen on that carbon, we can replace the H with a chlorine, and that'll give us a product. The only annoying thing about this is at every position, you certainly could have repeated structures. So the best thing to do is just go one by one and just at each carbon, let's replace one of the H's. Here there's 3 H's coming off, replace one with a chlorine. And then move your way down the chain very systematically, very carefully, not to skip any carbons. And then in the end, we'll make sure we didn't repeat any carbons either. So what about in the middle of the chain? If we had a chlorine here, okay, that could be an option, right? There was one H there, and we could switch it out with a chlorine. So keep going down the chain. Don't skip any carbons. At the top, if we replace one of those H's with a chlorine, we get this. Now, if you're looking ahead and you're like, are one of these repeated? We'll get back to that in a second. Just keep going down the chain, though. So next carbon down the chain. Here, if I replace one of these H's, the only H there, with a chlorine, I get another product. And then again, one more, well, actually two more here. At the bottom of the carbon chain, if I replace an H with a chlorine, I get this. And then last one here on the far right-hand side, if I replace an H with a chlorine, I get this. Okay, so the question is, how many of these are unique? When you're looking for unique, unless you have a problem specifically saying stereoisomers don't matter or something like that, we need to look for unique stereoisomers as well as structural isomers, meaning things that could be on the same carbon. If we're just moved one carbon down the chain, that's a different structural isomer now. So here, this is a primary alkyl halide. This is a primary alkyl halide. This is a tertiary alkyl halide. I know for a fact that tertiary is different. The question is, are the primaries the same? In this case, the answer is yes, because if I spin that bond right there, remember alkanes can spin freely, that would be the exact same thing as this structure. If you're struggling to visualize it, name it. If you name this one, you could argue this is a chlorine on 1 and a methyl on 2. Same thing here, chlorine on 1, methyl on 2. So this is actually the exact same thing. I'm going to go ahead and cross that out. What about this one? Well, that's tertiary, but it is the same as this, because again, if I were to name these, they'd have the exact same names, just going left to right versus right to left. So that is the same thing. So let's keep going. What about this one? Well, that's the same thing as this as well. It just literally flipped over. So that's actually a repeated structure. And then last one, this is also the same as this one, which was the same as this one. So this is a nice symmetric structure. I just wanted to show you how, in a lot of cases, if there's symmetry, things cancel out and end up with only a couple unique products. Not always. That's why you want to draw these out. Now, in this case, we did not have stereoisomers. Let me give you a hypothetical here where I'm not going to go through all of the potential options one more time, but I am going to show you what if we had this molecule with Cl2 and light, or Cl2 and heat, either one. Really, it's the same idea. They both produce radicals. So let's say one of the products would be if I put a chlorine at this position. Sure, that's one of the products. This is a chiral center, which means whenever we create radicals, we have to consider, what if you put the chlorine on a wedge, and what if you put the chlorine on a dash? So like here, those are different. If they're different, draw them both. There's really no shortcut. There's no way to memorize this. Like, well, what if they start with symmetric and end with symmetric? If you draw them on a wedge and a dash, and they're the same thing, just flipped over, meaning if it was not a chiral center, then don't draw both. But here, that is a chiral center. There's no way to take this and flip the whole thing over and make it match up with this. Those are unique. You'd have to draw them both. And of course, there are other options here. I'm just drawing one to show you, like you could put the chlorine here and here like we saw before, but just to give you the options there. Okay, what about bromine? How is bromine different? Well, it's just really, really picky. Does it also, in theory, produce a product here? Yes, but like such a small extent, we don't even consider it unless you are specifically told to draw the primary option. Otherwise, though, bromine is so very picky, it only adds to the tertiary if we have tertiary, or it only adds to the secondary if there's no tertiary at all. So here, we could add a bromine to this position. That's one tertiary option. Or we could have put a bromine on this position over here. But like we just saw up above, those are the same thing. So these are the same thing repeated, which means this would give you one unique product, the tertiary alkyl bromide. So the difference is, again, both bromine and chlorine prefer a radical on the tertiary position, sure, but bromine is super picky. We're only going to get this. Whereas chlorine is not picky. You could have all of the different options, just make sure to get rid of repeated structures. So that's the difference really between chlorine and bromine. Otherwise, though, there's really not reactions of alkanes we deal with in this class. So that's it for right now. We'll go ahead and move on.